Hello everyone, this is your educator. So today we will discuss this particular new reaction of William Carruthers books. Okay, so let us discuss what exactly the reaction is. Okay, so here we can take n is equal to 0 to 4. We can take n is equal to 1. We can take n is equal to 2, we can take n is equal to 3, we can take n is equal to 4. Okay, up to 4 carbon we can increase and we can do the reaction with diethyl malonate, that is our active methylene compound. Active methylene compound. Okay, in the presence of sodium ethoxide and the solvent is ethanol. Okay, so let us discuss what exactly the reaction is. Okay, we will take 1 carbon, then we will take 2 carbon. Okay, likewise we will take and we will discuss the reaction. Okay, so let us understand, let's do the understanding about this particular new example of this particular Carruthers reference. Okay, so in the presence of this particular sodium ethoxide base, what exactly happens? This is the diethyl malonate. This is diethyl malonate, OET. Okay, this is the diethyl malonate. This is the diethyl malonate. This is the active methylene compound. So 2 protons are present over here. Okay, out of 2 protons we will abstract only 1. Like this. Okay, in the presence of sodium ethoxide, what will happen? Na plus OET minus, what is the solvent? Ethanol, ETOH. Okay, so we will basically use here this sodium ethoxide in the presence of this particular dry ethanol. Okay, dry ethanol. Okay, so in the first step, what will happen? Step number 1. Step 1, what will happen? This sodium ethoxide will abstract a proton and there is a formation of enolate anion. So we are discussing enolate anion, enolate chemistry. So we need to generate enolate ion system. So C double bond O, OET, double bond OET, O minus Na plus. So this Na plus will coordinate this particular anion. Now after generation of this particular enolate ion or anion, this is unstable, we know it very well. This is unstable in nature. Okay, this is unstable in nature. Okay, this is unstable in nature. Now in the second step, what we need to do? We need to take this particular 1,3 bromine system. Okay, 1,3 bromo, 1,3 dibromo propane. We will take first of all 1 carbon, 1, 2, 3. We will take 1,3 dibromo propane. We will take. Okay, now we will take and we will do the reaction with this particular diethyl malonate system. So let us take new slide and do the reaction. So this is our second step, step number 2. This is our step number 2. So this is diethyl malonate system, anion, diethyl malonate system, enolate of diethyl malonate, OET. Okay, now we will take only 1 carbon system. Okay, that is 1, 2, 3, 1,3 dibromo propane molecule. We will take and we will do the reaction. Now in the presence of this enolate anion, what will happen? First of all, what will happen? These will come back like this, and the C is going to attack on this particular electrophilic center, and this bromine will leave out from the reaction, and there is a formation of new carbon-carbon bond. Okay, so this bromine will leave out from the reaction, and there is a formation of C double bond O OET, C double bond O OET. There is a formation of new carbon-carbon bond. Okay, 1 2 3 4. Okay, so here new carbon-carbon bond between this and this carbon, 1 2 3 1 2 3. This is our bromine system. Okay, this is what we got the step number 2 product. So again, in the presence of sodium ethoxide, again in the presence of sodium ethoxide, what exactly happens here is we will use again sodium ethoxide system, or whatever the bromine which is generated in this particular reaction, it will take the proton. It will take the proton, and there is a formation of again enolate anion like this. So now this is our enolate anion system, O minus OET, C double bond O OET, and this is our system. Okay, so again it will attack on the within the molecule. This reaction takes place. Again it will attack on this sigma star orbital. So it will come back like this, and this pi bond will attack on this particular sigma star orbital, and this bromine will leave out from the reaction with pointing electrons, and there is a formation of this particular product. That OET and 1 2 3. That is 4-membered ring will generate over here. Okay, 1 2 3. There are these 3 carbons, and this carbon including 4-membered ring will generate over here like this. So this is our final product of this particular reaction. Okay, this is the final product of this particular reaction. Now if you increase the number of carbons, then 5-membered ring. Then if you increase the number of carbon system, then here the number will increase. Okay, here the number will increase. I will write it as a N. Okay, here N is equal to, we can take 1 2 3 4 likewise. Okay, so this is how the reaction takes place generally. Okay, now let us discuss the next example of the Carruthers reference. So this is our next example. Okay, let us discuss the next example of this particular Carruthers reference. Okay, now what is the substrate? Substrate is bromobenzene. Substrate is bromobenzene in the presence of sodamide, Na plus NH2 minus. Sodamide in the presence sodamide. So this is called as sodium amide or sodamide in the presence of liquid ammonia. Okay, what is the intermediate? Intermediate is a benzyne. And when this benzyne treated with diethyl malonate anion, okay, enolate of diethyl malonate. Okay, this when this benzyne treated with enolate anion of diethyl malonate, there is a formation of this particular intermediate, this particular anion system. So this is unstable. This is also intermediate. This is also intermediate because charge species anion is present over here. Okay, again it will take the proton from the solvent medium. And there is a formation of this particular product. Okay, this is our final product. So let us discuss the mechanism of this particular reaction. So step number one. So first of all, when this bromobenzene, when this bromobenzene, so when this bromobenzene treated with sodium amide, okay, this benzene, bromobenzene when treated with sodium amide, Na plus NH2 minus, this is a strong base, very very strong base in the presence of liquid ammonia. Okay, what will happen? It will abstract proton from this side or this side. Okay, so we have not so we not did the isotopic labeling, so randomly we can pick up any proton, this one proton or this second proton. Okay, so this sodium amide is a strong base, very very strong base. Okay, so it will abstract a proton from this side and it will come back and it will form one pi bond, and at the same time this bromine will leave out from the bonding electrons. This bromine will leave out the bonding electron, minus Br will leave out from the reaction. Again this bromine will take the proton from the solvent media and leave it as a HBr molecule, leave out as a HBr molecule. Okay, leave out as a HBr molecule. Okay, this bromine will leave out as a HBr molecule, or bromide will leave out from the reaction. Okay, HBr molecule will leave out from the reaction, hydrogen bromide. Okay, and there is a formation of benzyne molecule, there is a formation of benzyne intermediate, benzyne intermediate. Okay, so this is the step number 1. So step number 2 we will discuss in the next slide. Okay, so step number 2, so this is the benzyne intermediate. So this is benzyne intermediate. So in this benzyne intermediate treated with diethyl malonate anion system or enolate of diethyl malonate. Okay, so this is our active methylene compound. So this is our active methylene compound, enolate anion, OET double bond O. So again this, whatever the negative charge which is generated on this oxygen, it will come back like this, and this will attack on this particular electrophilic center, and this will open up like this, and there is a formation of this particular molecule. OET. So here one anion is generated. Okay, so two lone pairs and two lone pairs which are present on the oxygen. So whatever the anion which is, so still it is unstable because charge species are unstable. So still it is unstable. Why? Because charge species are unstable. Again, when it will take the proton from the solvent medium. Okay, it will take the proton from the solvent medium or NH4 plus. Okay, NH4 plus. It will take the proton from the NH4 plus. So it will take the proton like this. Okay, and there is a generation of this particular system. Okay, this particular system, C double bond O, OET. So there is a generation of this particular product. Okay, so there is a generation of this particular product. This is our final product. So this is act as a good nucleophile. This is our good nucleophile, and this is our unstable benzyne molecule, benzyne intermediate. So still these two carbons are sp2 in nature, sp2, and this carbon also sp2 in nature. This is not at all sp. Okay, this is sp2 in nature. Okay, this is a weak interaction between these two sp2 center. Are you understanding my point? So this is our mechanism of this particular reaction. So let us discuss the further example. So this is our new reaction. So what exactly the reaction is? They have mentioned this particular substrate. This is our substrate in the presence of same condition, sodium methoxide, base. This is the base, and this is our solvent. And this is a dry medium. Okay, dry solvent we have taken. Why we have taken dry solvent in the drastic condition? It is just because of it has a proton, so this base can take the proton easily. Okay, so in the presence of dry solvent, this reaction is taking place over here. Okay, so our system is naked in nature. Okay, highly unstable and strong base. Sodium methoxide is a strong base. Okay, so what exactly happens here is sodium methoxide. So there are two types of protons, acidic protons. This is one acidic proton, and this is also acidic side. So here 3 acidic protons are present. Okay, so base will abstract proton from out of two sides. It will abstract proton from one side, because both sides are symmetrical in nature. So we have added base will take one proton, and there is a formation of anion system. So this anion will delocalize like this, and these anions will come over here on the adjacent to this particular electron withdrawing system. And this anion is effective. Now this anion will attack on the methyl iodide. Iodine will leave out from the reaction, and there is a formation of again carbon-carbon bond formation reaction. Again there is a formation of new carbon-carbon bond. So this is the carbon-carbon bond formation reaction. So this is carbon-carbon bond formation reaction. So in the enolate chemistry, what we are learning? Carbon-carbon bond formation reaction. We are studying carbon-carbon bond formation reaction. We are studying alkylation. Okay, we are studying alkylation. Okay, so let us discuss the mechanism of this particular reaction. Okay, so step number 1, we will discuss step number 1. So in the step number one we will discuss. So this is alpha beta unsaturated compound, C triple bond N, and this is C double bond OET. So this is the alpha carbon, this is the beta carbon, alpha beta unsaturated compound. Okay, in the presence of base, what will happen? Sodium methoxide, sodium OET, methoxide. What will happen? Okay, it will take proton from the one of the, out of two sides, it will take proton from the one side. Okay, so it will take the proton. Let us suppose it has taken proton from this side, like this. This bond will break like this. Okay, this bond will break like this. So I will show in the only one step. Okay, so this, after abstracting this particular proton, there is a formation of anion system over here, and this anion, when do the conjugation, this pi bond will break and this will come over here. Okay, now what happened? There is a generation of this particular C triple bond N, and COOET. So this is the minus charge generated over here. So this is our main system, okay, active system. This is our active system. So alkylation will not take place from the alpha, beta, gamma carbon. So this is the alpha system, this is the beta system, and this is the gamma system. So alkylation will take place from the alpha position, because alpha position is the most active in nature, because it is adjacent to the 2 electron withdrawing group. Okay, so it cannot go over here, it cannot move further, and it can't do the alkylation from the gamma side. It will attack from the alpha side, because here anion is much more stable. So anion will not do the further conjugation. Anion will itself will attack from this side. Okay, so this is our main system, active system. It will attack from the gamma side, alpha carbon. Okay, it will attack from the alpha carbon. So let us discuss the next step in the new slide. Okay, let us discuss the new step. So what we have generated, step number second. What we have generated? So we have generated this particular compound. Okay, we have generated this particular compound, COOET, and here C triple bond N is present over here. So this is the methyl system, and this is the anion over here. So this anion can further do the conjugation like this. Okay, and there is a formation of another canonical structure, O minus OET, double bond over here. Okay, double bond over here like this. Okay, double bond system over here like this, and here C triple bond N is present over here. So in the presence of methyl iodide, what will happen? So this iodine will pull electron, because more electron in nature. So iodine will pull electron towards itself, due to which delta minus del positive charge which will generate on the adjacent carbon atom. Okay, so this iodine will withdraw electron density from this particular carbon. So this carbon becomes slight del positive, electrophilic in nature. So again it will come back from this side. It will not directly attack from the oxygen, because oxygen is harder in nature. Oxygen is hard in nature, and this carbon is soft in nature. This carbon is soft in nature. So soft, and this is also act as a soft electrophile. Okay, so soft interactions, soft plus soft interactions, soft interactions are, you can say, better in nature. Soft interactions better in nature, or soft only do the reactions, not hard and soft. So soft interactions are better in nature, not a hard soft. Okay, like this. Likewise, we have to understand hard reagent will react with a hard center, and soft reagent will react with a soft center. So this is the hard site. It won't attack from this side, because this is softer in nature, because this is not a good interaction. So hard interactions are better rather than hard soft. Okay, so again it will come back like this. So this nucleophile will attack on the electrophilic center, and this will leave out from the reaction. And there is a formation of so iodine will leave out from the reaction, and there is a formation of this particular molecule over here. So there is a formation of, so there here C triple bond N cyanide is also present, and here methyl will come here. So this is the hybridization of this particular center is sp3. Okay, so this is our final product. This is our final product. Are you understanding my point? Okay, let us discuss the new example of this particular Carruthers reference. New example of this particular Carruthers reference. So again, same, this diethyl malonate which is present over here. Again, what we have taken? Diethyl malonate. Okay, diethyl malonate we have taken. This is active methylene compound. Active methylene compound. Okay, so this active methylene compound, again when we do a reaction with the sodium methoxide, what will happen? Enolate will generate, and this enolate is going to attack on this particular alkyl halide. After formation of new carbon-carbon sigma bond, we have two types of reactions. That is, we have two types of reaction. That is neutral decarboxylation, and another one is a basic neutral decarboxylation, and another one is a after formation of acid. Okay, acid hydrolysis. After acid hydrolysis, we can do the just simply heat the reaction in the presence of basic medium, or in the after doing the hydrolysis, there is a formation of two carboxylic acids, two carboxylic group, and out of two carboxylic group, when we heat slide in the presence of acid, what will happen? One of the carboxylic group will leave out from the reaction, and there is a formation of this particular final product. So that's we need to discuss here. So this is the neutral decarboxylation. This is hydrolysis. After hydrolysis, decarboxylation. So there are two types of decarboxylation. Neutral means in this particular state, lithium chloride will attack on the ester group, and one decarboxylation will happen, and there is a formation of this particular ester only. So in the neutral decarboxylation, we have remains this ester group is present. Okay, but in the basic hydrolysis, after doing the basic hydrolysis, we got carboxylic acid. Okay, after doing the decarboxylation. Okay, let us discuss the mechanism of this particular reaction. So as simple as we can understand like this. Okay, let us discuss the step number 1. So what is the active methylene compound? Diethyl malonate. So this is the diethyl malonate. Okay, so it has proton in the presence of sodium methoxide. What will happen? This sodium methoxide will take the proton, same procedure, and there is a formation of enolate anion. There is a formation of O minus Na plus C double bond O, OET and OET. Okay, so this is the enolate ion. Okay, so this is the enolate ion. When this enolate ion reacted with alkyl halide, we can take alkyl halide. So this is halogen. Halogen is equal to chloride, bromide, iodide. Okay, like this, chloride, bromide, iodide. Okay, so this is act as a nucleophile. This is act as a nucleophile. Okay, let us discuss the step number 2. We will do the step number 2. So we have generated enolate system. So we will do the step number 2 in the next slide. Okay, we will do the step number 2 in the next slide. So let us discuss the next step of this particular reaction. So next step is basically, so we will discuss next step. Step number 2. Okay, so this is our enolate anion, O minus OET, C double bond O, OET. Okay, in the presence of alkyl halide. Rx. X is equal to chloride, bromide and iodine. Chlorine, you can take chlorine, bromine, or you can take iodine. Okay, so these halides are more electronegative in nature, so this is more electronegative, more electronegative, more electronegative. So this is more electronegative, so it will pull electron towards itself. Apply inductive effect over here. So when we pull electron itself, there is a formation of del minus charge. Okay, it becomes a rich, electron rich. Del minus charge will come on this halide, and it will slightly create electrophilicity on this particular carbon of this particular alkyl system. Now at the same time, what will happen? This anion will delocalize like this. This can come back. Okay, this will come back like this, and this is going to attack on this sigma star orbital of this particular carbon halogen bond. Okay, exactly opposite to this particular sigma bond. One sigma star orbital is present over here, sigma star orbital is present over here. So this attack will take place on the sigma star orbital. Okay, so and there is a formation of so this is our diethyl valonate system, this is our diethyl valonate system, OET. Okay, so R is generated over here, R is came over here. Okay, this is the carbon-carbon new bond formation. So what we did, carbon-carbon bond formation, reaction we did. Okay, after formation of this particular carbon-carbon new bond, carbon-carbon new bond, what we need to do, we need to remove the one carboxylate group. Okay, one ester group we need to remove. Or so there are two possibilities. We can do hydrolysis and we can do decarboxylation, or we can do the neutral decarboxylation. Okay, so let us discuss this step number 3. Step number 3 of this particular reaction. Step number 3. So step number 3 is so we have generated this particular OET, R C double bond O, OET. Now what we need to do, we have two possibilities. We have let us discuss the possibility number 1, pathway number 1, that is neutral decarboxylation. Okay, so in the neutral decarboxylation reaction, so what is the reagent? Lithium chloride, lithium plus Cl minus, lithium chloride. Okay, when we use lithium chloride, what will happen? Neutral decarboxylation takes place. Neutral decarboxylation in the presence of polar aprotic solvent. DMF, dimethyl formamide, formamide we can take, dimethyl formamide. So structure of the dimethyl formamide is C double bond O, AH, and we can take N here, NN dimethyl formamide. So this is the NN dimethyl formamide. So this is the polar aprotic solvent, and good solvent. Okay, so in the presence of lithium chloride, what will happen? Neutral decarboxylation will happen. How this reaction takes place? Let us discuss. Let us discuss. So this is our I will open it. Okay, slightly I will open it. So it has gone now. Simply what I will do, I will directly use this particular lithium chloride. Okay, now this lithium chloride, what will happen? First of all, chelation will happen. This oxygen will do the chelation, and at the same time what will happen, this lithium will attack on the electrophile, this carbon system, and at the same time the bond between this carbon will break like this. It will break like this, and this bond will break and it will come over here, and this bond will open up like this. Okay, so what leave out from this reaction? What will leave out from the reaction? EtCl, ethyl chloride is a gas. It will leave out from the reaction, as well as carbon dioxide is a gas. It will leave out from the reaction, and there is a formation of this particular system, R O minus OET. Okay, so there is a formation of this particular intermediate. So when we do the acidification, what will happen? It will take the proton. So we can use simple bases like this, simple acids, dilute HCl we can use. Okay, or we can use water. Okay, or we need to do workup we need to do. Okay, after doing the workup, what will happen? There is a formation of OET, bond, okay, alkyl system, OAH. Now what will happen? Tautomerism will happen. Okay, tautomerism will happen, and there is a formation of R C double bond O OET, and so this is what generated in the system. So this is our A product. This is our product, one of the product. Okay, this has been formed by the neutral decarboxylation. Now in the presence of basic hydrolysis, if we do the basic hydrolysis, then the that reaction is a different term. Okay, let us discuss that particular pathway number B reaction. Okay, so this is our substituted or carbon-carbon bond formation after doing the carbon-carbon bond formation reaction. This is our substituted diethyl malonate system. So what we need to do? We need to do simply in the presence of sodium hydroxide. What we need to do? Basic hydrolysis we need to do. So if you add base, what will happen? This is a nucleophilic base, act as a nucleophile. It will attack on the electrophilic center. This bond will open up like this. And again there is a formation of O minus system, OET system, and OH is attacked on this particular system. Okay, now again this will come back like this. OH is a weak leaving group. Sodium methoxide is a somewhat a leaving character. It will leave out from the reaction. OET minus will leave out from the reaction, and there is a formation of this particular product. Okay, this particular carboxylic product like this. Again, what will happen? Only one molecule is not we have added. So only one we have used more than one equivalent. Okay, sufficient sodium hydroxide we have used. Okay, so what will happen after formation of this carboxylic acid? Again the reaction will take place on the this center also. Okay, simultaneously, or we can say after this group, when this group reacts, and then this group will react. Okay, first of all we did the mechanism of this particular ester group is converted into this particular carboxylic group. Okay, this particular carboxylic group. Okay, so again in the presence of sodium methoxide, sodium hydroxide, what will happen? This will attack on this particular electrophilic center. This will open up. Again this will come back and it will leave out from the reaction. OET minus will leave out from the reaction, and there is a formation of carboxylic acid, and this is substitution which is present over here. Now in the presence of H3O plus, in the presence of heat, if you do the if you heat this particular reaction, in the slight acidic condition. Okay, in the slight acidic condition. Okay, this is not our final product. Okay, are you understanding my point? This is not our final product. This is not our final product. Again the base, again these ethoxide ion, 2OET minus ions will take the proton, will abstract the proton. Okay, both protons, and leave out as a ETOH, leave out as a ETOH, and there is a formation of C double bond O, O minus, C double bond O, O minus. Okay, O minus, Na plus will come, Na plus will come over here also. Okay, this is the substitution we did. Okay, so in the presence of H3O plus, in, okay, if you do the H3O plus in the first step, what we need to do? H3O plus. We will do the H3O plus reaction. Okay, when we treat this particular compound intermediate, so this is the intermediate, intermediate, it is just because of this is the unstable. Okay, high resonance is present over here. Okay, these groups are continuously doing the resonance. So when we this unstable system, when we do the hydrolysis, or when we do the acidification, or when we do the workup condition, okay, acidification reaction, acidification reaction, when we do the acidification reaction, what will happen? Simply it will take the proton. So this will take the proton from the hydronium system, and this will take the proton from the hydronium system. Okay, and there is a formation of this particular carboxylic acid molecule. Okay, there is formation of carboxylic acid. Okay, this is substitution what we already discussed in the first step of the mechanism. Okay, so this is the carboxylic acid. So when this carboxylic acid generates over here, what we need to do? Simply we need to heat this particular reaction. So let us discuss the step number 2 of this particular decarboxylation. So this is the step number 1. Let us discuss the step number 2, that is decarboxylation. Okay, let us discuss the decarboxylation reaction. So what we have generated? Step number 2, what we have generated? We have generated this particular system, C double bond O OH, C double bond O OH system, and C double bond O OH system. Okay, and this is the alkyl system. Okay, simply when we heat this particular molecule, what will happen? This proton will leave out from the reaction, formation of new pi bond will take place over here, and this system will this sigma bond will break, and this will open up like this. There is a formation of pi bond system in between this particular carbon and this carbon, and carboxylic group will leave out from the reaction. Carboxylic acid is very stable molecule. Okay, gas, it is gas, it will leave out from the reaction, as well as what will happen? H plus will leave out from the reaction. Okay, or you can think like this, or you can think like this. This is the carboxylic group OH, this is the carboxylic group, this is our substitution, you can think like this also, C double bond O OH. Okay, OH. So you can think like this also. When we heat this particular molecule, these non-bonding electrons will attack on the sigma star orbital, and it attacked on the sigma star orbital of this particular oxygen hydrogen bond. This sigma bond will break, and this sigma bond will break, and there is a formation of anion system over here. Okay, anion system over here, like this, O minus anion system over here. It has taken proton like this. Okay, so after this particular process, again whatever the anion which is generated over here, it is unstable. Again, what is the condition? Heat. We are heating this particular reaction, reaction medium. Now again this charge will move further like this. So there is a formation of bond between oxygen and carbon. So when this bond will form, it has to break this old pi bond like this, and this pi bond will shift on the oxygen, because here formation of carbon-carbon new pi bond will take place. So it has to break old pi bond, then and then only we can satisfy the valence of the carbon system. Okay, so because valence of the carbon is 4, due to valence of the carbon is 4, we need to break this old pi bond, then and then only the reaction will valid in the inverse of organic chemistry. So what we have generated, minus carboxylic acid will leave out from the reaction, and there is a formation of C double bond O, OH and OH. Okay, so what will happen now? Tautomerism will happen. Okay, tautomerism will happen. Tautomerism will happen. Okay, so this will come like this. This sigma bond will break like this, and this pi bond will take the proton. So intermolecular tautomerism will happen like this, and there is substitution is there. Don't forget this. Substitution is there. Don't forget to write the substitution. Okay, so tautomerism will happen. And why tautomerism will happen? It is just because of the bond energy of this particular carbonyl. Bond energy of this particular carbonyl is more. Okay, bond energy of this particular carbonyl is more. Okay, as compared to this carbon, oxygen sigma bond, this carbon and oxygen having double bond system, and this C double bond O has more bond energy, more bond energy. So that is why it will this enol form is not at all stable. It is converted into the keto form. So this is the keto form. So this is the carboxylic acid, what keto form. So this is the carboxylic acid what we got. So this is our final product. This is our final product. Are you understanding? If you have questions, you can write in the comment box. Okay, so let us discuss the further example. Now, so this is the new reaction. We will discuss this particular reaction. Okay, this is the new reaction coming in Carruthers reference. Okay, so this is the new reaction. So this is what we need to discuss now. Now, what is the substrate? This is the substrate. This is our substrate. Okay, this is our substrate. Okay, okay, this is substrate. What is the substrate? Ester. We have ester. Okay, and what is the reaction condition? What is the reaction condition? Lithium diisopropyl amide. So this is the base, lithium diisopropyl amide. What is this? This is base. Okay, lithium diisopropyl amide. Okay, which type of base it is? This is a non-nucleophilic base. Non-nucleophilic base. This is the non-nucleophilic base. So it is not at all act as a nucleophile. It is strongly act as a base. Okay, strongly act as a base. Okay, so in the presence of tetrahydrofuran, and what is the temperature? Minus 78 degrees Celsius. Minus 78 degrees Celsius we need to maintain. Then and then only this reaction takes place desiredly. Okay, and in the next step we have taken allyl bromide. Okay, so what we need to generate? We need to generate elevate anion in the presence of this particular strong non-nucleophilic base. So let us discuss the mechanism of this particular reaction. So this is very simple. So this is our substrate. What is the substrate? How many carbons are there? 1, 2, 3, 4, 5 carbons are there. Okay, 5 carbons are there. So this is the ester, 5 carbons are there. So this is the ester, 5 carbons are there. 1, 2, 3, 4, 5 carbons are there. O, M, E. Okay, So in this particular substrate, we have to do the, so this substrate when treated with lithium diisopropyl amide, so this is lithium diisopropyl amide. Okay, lithium plus diisopropyl amide. Okay, so this is the non-nucleophilic base. That means it is not at all it will not at all act as a nucleophile. So simply it will take the proton from the alpha carbon of this particular ester. There is a formation of anion on this particular carbon. Okay, there is a formation of anion on this particular carbon, OMe. There is a formation of an anion system over here. This anion delocalizes because on the carbon negative charge is unstable. Okay, negative charge is unstable, very unstable. Carbon can't hold this particular charge. That is why it will transfer. That is why it will do the delocalization and it will transfer charge on the more electronegative group. On more electronegative group, negative charge is stable. Negative charge is stable. That is why it is doing delocalization. So it is not act as a nucleophile. This is non-nucleophilic base. It is not at all act as a nucleophilic base. So this is non-nucleophilic base in the presence of tetrahydrofuran. Okay, in the presence of tetrahydrofuran. So this is the tetrahydrofuran. Okay, minus 78 degrees Celsius we need to maintain here. So there is a formation of enolate anion. So that enolate anion we will write in the O minus OMe. Okay, first, second, third, fourth and fifth. Okay, this is our substrate. Okay, enolate anion or ion. Okay, so this is the further step. Okay, so this is step number 1. We generated enolate anion. So this enolate anion, you know it very well, unstable. This enolate anion is unstable. This enolate anion reacting with allyl bromide. So it is going to attack on the sigma star orbital of this particular carbon bromine bond. So this is the allyl bromide. Okay, this is the allyl bromide. So this is the sigma star orbital, exactly opposite to this particular sigma bond. Sigma star orbital is present. Okay, so there is two possibilities. So nucleophile can, or the substrate nucleophile, this is act as a nucleophile, can attack on this particular sigma star orbital, or it can attack on the pi star orbitals of this particular sp2 center, pi star orbital. So it can attack on the pi star orbital. Okay, so if it is attacked on the sigma star orbital, if it is attacking on the sigma star orbital, then also same product we will get. Then also we will get same product. 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 And if this nucleophile attacks on this particular sigma star orbital of this particular carbon bromine bond, then also we will get same product. We will get same product. You need to understand this particular. So if this nucleophile attacks on this particular sigma star orbital, then this is called as SN2 reaction. And if this particular nucleophile attacks on this particular pi star orbital of this particular sp2 center of this particular allyl bromide, aryl bromide system, then this is called as SN2. This is called as SN2 prime reaction or SN2 dash reaction. SN2 dash reaction. Are you understanding my point? So anyhow, it will attack. It is not at all stable. That is why this reaction is happening. So this is now activated. This is act as a nucleophile. It is come back like this. It will come back like this, and this nucleophile will attack on this particular pi star orbital, or this nucleophile can attack, or this nucleophile can attack on the sigma star orbital. Same product we can got. We will get same product. We will get same product. Okay. So what is the product? What is the product? COOMe. So 1, 2, 3, 4, 5. Okay. Whatever substrate we written, it is correct. Now substitution takes place at alpha carbon. Alpha carbon. This is beta carbon. This is the gamma carbon. This is the delta carbon. Okay. So substitution takes place at second position, that is alpha position. So this is our allyl system. This is our allyl system. Okay. So this is what our final product. This is what our final product. This is what our final product that we need to understand. Okay. Let us take this screenshot of this particular reaction. Let us take this screenshot of this particular reaction. So after doing this particular reaction, again in the presence of lithium diisopropylamide, again what they have mentioned, again we need to carry out further reaction. Again we have to treat this particular compound with a lithium diisopropylamide in the presence of same condition, tetrahydrofuran minus 78 degrees Celsius, and second step is a ethyl bromide, and second step is a ethyl bromide system. Okay, this is act as a, this is our alkyl halide. This is our alkyl halide. Okay, so again further we can do the reaction, because this alpha carbon having another removable proton, that is acidic proton. Okay, it is having another alpha proton. Okay, that is why we can do the further reaction. So again what we need to do, again whatever the substrate which is generated, over here, that we need to treat with this particular reaction condition, and we have to generate this particular final product. So this is our final product. So how this reaction takes place, let us discuss. Let us come to the next slide. So what is the product? So this is the second reaction now. Second reaction. Okay. So product first. What is the first product? This is our first product. C double bond O, OMe 1. So second position, here we substituted allyl bromide. Okay. This we did alkylation, and 1, 2, 3, 4 and 5. This is the fifth carbon. So this is our substrate. Okay, product. This is first step product. Step first product treated with LDA. Okay, so LDA is a strong non-nucleophilic base. LDA is strong non-nucleophilic base. So this is the LDA. We know it very well. This is LDA minus lithium plus. Okay, so this LDA will take the proton. This is the alpha proton, acidic in nature. Okay, again this will generate enolate anion. Again this will generate enolate anion. That we need to understand. O minus, and whatever the enolate anion which is generated over here, that is treated with the ethyl halide. Okay, ethyl bromide, that is treated with the ethyl bromide. Okay, that is treated with the ethyl bromide. So it will attack on the sigma star orbital of this particular ethyl bromide. So what is the reaction condition? Tetrahydrofuran in the presence of minus 78 degrees Celsius we need to maintain during the reaction. Then and then only the reaction will takes place. Okay, then and then only the reaction takes place. Okay, so after formation of this particular product, we need to treat this particular alkyl halide. We need to do the reaction with this particular alkyl halide. So this will come back like this, and this nucleophile will attack on this particular electrophilic center, and this bromide will leave out from the reaction. And we are going to get, and what we are going to get? We are going to get this particular compound. We are going to get this particular compound. So this is our final product. That we need to understand. So if you have questions, what is which reaction it is? It is the SN2 process, SN2 reaction. Understanding? Biomolecular nucleophilic substitution reaction. Okay, so this is what the final product. So we will stop here. Next reaction we will discuss in the next video lecture. Thank you very much for watching the video. Please do remember this particular reaction, and please do watch, and please do share, like, share, subscribe to my channel. Thank you very much for watching the video.